Science and fiction both discuss megastructures, immense constructions in space at scales which allow them to participate in the interplay of celestial forces. The first megastructures were designed some 50 years ago by Dr. Gerard K. O'Neill and have been revised and revisited extensively since then. The kilometer-long O'Neill cylinder, the Stanford Torus, the Niven ring, the Dyson swarm, thought experiments of engineering which might take millennia to realize, these are often discussed projects for humans of the far, far future. Today on Demystifying, we're discussing a new megastructure designed around near-term human technologies. The goal here is to place 1 million people beyond the orbit of Mars within the next 200 years while respecting physics and engineering limitations. The target of our discussions today will be the dwarf planet Ceres, a body often recognized as a gateway to colonizing the outer planets, including the moons of Jupiter and Saturn. Ceres is unique. It is an example of a world at the edge of the habitable zone and serves as a window into the prehistory of our own world. It will show us how habitable planets form, and close study of this world is arguably required to correctly ascertain the properties of habitable exoplanets. In human terms, Ceres can be thought of as a kinder Luna, with roughly the same surface area as the country Argentina. Located on the asteroid belt, it is on average 3 times farther from the Sun than Earth is, making it a safer radiation environment than Earth's moon. Still, it is closer to the Sun than other icy bodies in our solar system, allowing it to sustain melted ice in its interior without a highly active core or geology. Receiving about 1/10 of the sunlight that we receive on Earth, solar panels are still effective in this location. While discussions of colonization of Mars are prevalent today, there are convincing reasons to pursue a human colony on Ceres before colonizing Mars or even our moon. While a Hohmann transfer to Mars can occur only about every 2.1 years, missions to Ceres can be launched every 1.2 years. The low gravity and location of the planet means that transporting cargo to Ceres from Mars, or from the Moon, is more energy efficient than transportation from Earth to the Moon. When humans become capable of manufacturing in space, there will be no reason to pursue Mars or even the Moon as a first long-term settlement. Settling Ceres with a population that can remain stable for hundreds of years will be mankind's top priority after we test our technologies for settlement on Luna. Ceres has plentiful water ice, and its partially frozen internal ocean heats and pushes melted water through the planet's crust, producing hydrated clays. The body once had an ocean on its surface with strong hydrothermal activity, and remnants of these features lay just below the surface. Today, the dwarf planet has a fine regolith exterior, making processing, construction, and mining easier than on worlds with a hard, icy surface. The regolith on Ceres can be likened to the lunar variety, but with more porous and abundant water ices locked within. The planet is large in geophysical terms. It is much larger than most bodies of an equivalent mass due to an abundance of water ice. Earth is about 0.1% water by volume, Mars is 0.05. Ceres is over 40% water, with most of this mass extant in the core and mantle. On the surface, water ice is concentrated at the poles, with the equatorial regolith containing less than 1% water. Most of the non-hydrated regolith originates from meteor bombardments and has been desiccated by solar radiation. Ceres has been described as a chemical factory, with models describing up to 20% of the planet's crust as being carbon compounds distributed in damp clay. Crucially, the surface of Ceres is an ample source of amorphous carbon, perhaps in a more concentrated form than any other location in the asteroid belt. Amorphous carbon is a vital resource for future construction projects and producing human materials such as soil. Studies indicate the upper crust of Ceres was created by the bombardment of carbonaceous chondrite meteorites, which contain more diversity of material than most other meteorites. With carbon, water, and useful volatiles existing in abundance in the near surface, Ceres has clear advantages over other bodies for mining and industry. Orbital assets will no doubt be established as Ceres is colonized, but they will not be directly necessary for the survival of humans, with a major exception. We will discuss this exception in detail first and ignore various temporary orbital installations, such as fuel depots, layover stations, and worker habitats for now. We can and likely will utilize the opposition effect to increase available solar energy on the surface of Ceres by utilizing a solar collector mirror. All bodies with a fine regolith surface behave like a reflective lens when exposed to sunlight. This effect, when paired with an orbital reflector, allows light reflected from Ceres to be focused and bounced back at its surface for collection by solar power arrays or use in agriculture. The small size of Ceres might allow humans to establish the first successful solar lens in a stationary orbit at the Sol Ceres L1 Lagrange point. The unique environment of Ceres' orbit allows this solar lens to be practical when it otherwise would fail to function in lunar orbit or around one of the Jovian moons, to name two examples. The planet is very small and has low gravity, and unlike most dwarf bodies which end up as moons, Ceres has no gravitational competitors nearby to destabilize long-term satellites we might put in its orbit. A solar lens around Ceres will need to be relatively far from the body to remain in a stable position. This is a problem on other bodies, but here it instead provides additional benefit. A solar lens blocks incoming sunlight, so it should not be too large, or it will reduce its own available energy. Yet, it should appear as large as possible when viewed from the surface of Ceres, so that it can reflect the most light back to the planet. This means there is a balance of lens size and distance which must be achieved, and Ceres is uniquely positioned to take advantage of this synergy. The solar lens would maintain its position several thousand kilometers from the surface of Ceres. This is just at the edge of a stable L1 orbit, demanding regular station keeping to keep the lens from losing stability and floating off into deep space. The thrust needed for these station-keeping maneuvers is provided by a set of sails which angle to capture the sun's photon pressure. This allows the lens to remain effective for up to hundreds of years in theory. The lens itself can be a simple design, a thin reflective material a few thousandths of a millimeter thick and several hundred meters wide. Holes and tears resulting from micrometeorite impacts are unavoidable and ultimately less of a problem than any momentum received from their impacts on the sail. So the choice for a larger but thinner shield over a more durable and massive one seems obvious. Too much extra momentum from collisions with space debris will require maneuvers taking up to months to correct, since the thrust from photon pressure is low. The majority of Cererians inhabit a region known as Synodal Alley, a concentric network of submerged habitats arranged like spokes around the metropolis known as Base Camp. Unlike on the Moon, where infrastructure was developed in many locations on the equator simultaneously, 99% of all man-made structures on Ceres reside in the Karawan Basin just south of the equator in the Vendemia Planitia region. A localized human presence is practical here, since geographic locations provide fewer benefits than on other bodies such as Luna. This mostly has to do with the planet's day length and distribution of resources across its surface. The Sun transits across the Cererian sky over the course of just 4 hours, followed by 5 hours of frigid night. Human surface activity is limited in this environment due to concerns about thermal shock affecting equipment, so most transportation occurs on underground railways. Each habitat on Ceres, of which there are 3 as of 2225, were built using similar techniques. These habitats are similar to those used in the colonization of the Moon over the last 200 years, but scaled up and utilizing more powerful construction tools, as well as provisioning for artificial gravity. Each structure provides about 1.05 square kilometers of farmland. The Haworthia-style habitat begins as an excavation using low-yield nuclear devices. A circular pit 1 kilometer across and half or a quarter a kilometer in depth is cut into the regolith with the assistance of several detonations. Large pieces of debris produced by these excavations, which might end up on dangerous orbits, are mostly avoided by using nuclear devices underground, which vaporize rock instead of blasting it apart. Any debris ending up at the bottom of the site will be quarried using traditional techniques and used as gravel and foundation material. The high thermal output of this process creates a rigid wall and foundation to the pit. Just after excavation, molten rock will form a radioactive slurry at the bottom of the pit, which quickly evaporates and forms a thick foundation. This surface is still radioactive, and so a layer of regolith gravel is added, with finer regolith on top. The top layer of material is mixed with cementing compounds and then cured with solar energy to form the floor of the habitat. While waterproof, resistant, and tough, this flooring can be removed and reshaped. Water is added to the gravel layer and will block radiation from entering the construction site in the short term. A large disk will form the habitat's floating foundation. This component is made of a regolith concrete slab baked by intense thermal loads of a nuclear blast. The concrete has layers of material high in metal content between rocky layers, with the individual layers becoming cemented together thermally. Unlike the material several hundred meters under the habitat, this disk was not in proximity to a nuclear device. It can be likened to a wafer of concrete and thin layers of very impure steel cut and shaped by industrial processes. Reinforcements are added, including sintered steel wire and rebar, as well as regolith cement to fill in any gaps. This structure needs to stand the test of time. It does not need to be homogeneous and might have weight irregularities. The disk is lowered into the pit, supported by scaffolding before being put into final position. The remaining structural parts of the habitat are assembled inside the pit and then attached to the disk, forming a large bowl. These include compartments and terraces designed to take advantage of light entering the habitat from above. At this point in construction, the bowl-shaped terraces would be filled with more gravel and retained with a metal mesh, providing a foundation for soil and drainage media. This ballast also balances the disk, ensuring it sits level on the fluid bearing. As the disk is being constructed, the pit is gradually filled with salt water, which floats the disk on its surface. The water is kept warm by nuclear power plants, providing the worksite with power, both to prevent freezing and to provide the buoyancy needed to keep this massive slab of fused regolith afloat. When the habitat is finished, it will be able to regulate the temperature of the fluid bearing using solar energy. Any exposed water around the edge of the disk is sprayed with a flexible plastic film until construction is complete. The spraying is done using low-pressure gas, and the process takes advantage of surface tension to create an effective barrier. This film of material retaining the water is temporary and only acts to keep the water base stationary while construction continues above. The disk is still being held in position and will not feel the weight of gravity until the habitat is nearly complete and scaffolding is removed. The dig site is now covered, its interior still being accessible from the surface via smaller tunnels established around its edge. The covering is a grid of reinforced transparent panels locked in a honeycomb structure with a slightly concave geometry. The protective honeycomb dome, made of steel and reinforced basaltic glass, offers Cererians a secure window into space. Behind the protective barrier, a layer of water is pumped in and suspended. This is accomplished by placing a number of large plastic balloons against the roof, which attract the water via surface tension and evenly distributed across the entire ceiling. With gravity being as low as 0.03 Gs, very little is required to keep the water immobile against the roof of the habitat. Acoustic, thermal, or simple water flow are sufficient to stabilize a large volume of water suspended between the balloons until the habitat is ready to be pressurized. This volume of water is more part of the habitat's ecology than a strictly protective measure against radiation and micrometeorites. It directly influences weather in the colony, and acoustic and thermal excitation of the mass will provoke rainfall. The water column can be shaped using acoustics or by adding large gas-filled balloons. Rotation of the habitat on its fluid bearing produces air currents in the atmosphere, further contributing to keeping the water pocket self-supported. Control of air temperature gradients across the entire habitat exerts pressure on the water pocket as desired. The warm water produced by this system is passively forced down the walls of the habitat in grooves and maintains temperature of the fluid bearing below. This system operates without input, allowing a habitat to remain free-flowing even without electrical power. In practice, these grooves will become calcified and possibly even host to algae residues, but the higher flow rate of the water will prevent buildup to a degree. The addition of the water pocket forms an airtight seal at the top of the habitat, and the volume can then be pressurized with helium. A long process will soon follow, where organic material will be brought in and broken down in massive composting operations to satisfy the habitat's soil requirements. This will take several years, and over this period the habitat is closely monitored for structural weaknesses and undetected voids in the nearby regolith, which might threaten the structure's longevity. The floating disk is set into motion at the end of this process, picking up speed over the course of several months as the structure is monitored and tested. The habitable areas of Haworthia are arranged on the inner walls of the floating bowl-shaped structure, allowing the colonists to freely walk the total circumference of the habitat while enjoying up to 0.65 Gs. The terraced interior of the habitat will require a large amount of organic soil. Much of the soil material will be produced locally using cyanobacteria colonies and amorphous carbon. These bacteria will also work to provide a more oxygen-rich atmosphere once they are transplanted into the colony. Just a few years after construction begins, the habitat is ready to be populated with humans and a carefully selected ecology. The planet's surface immediately around the habitat is bathed by useful light, and a ring of reflectors are erected to focus sunlight onto the dome of the habitat, increasing efficiency even further. The habitat is spun up to 0.5 Gs, or 1 complete revolution per minute. The tangential velocity of the colony's outer edge reaches 52 meters per second. The air gap between the walls of the habitat and the fused regolith retaining wall will heat up and circulate hot air into the habitat, sustaining the colony's thermal needs. Contributing to this warming is the Coriolis effect, which is produced when centripetal acceleration is used to produce artificial gravity. The habitat is sufficiently lightweight to hold together at well over 0.5 Gs. Because most of the mass of the structure is contained in the centered structural disk, the habitat retains its rotational energy efficiently. Our design implies the habitat is much heavier at one end than the other, indicating a number of forces will attempt to throw off the rotation. This could lead to damage or destruction. The fluid bearing remedies this problem. Tangential forces are opposed by buoyancy of the colony, and excessive pressure on the fluid bearing will increase contact with the fluid, both slowing the rate of rotation while increasing its temperature via friction, thus increasing the buoyant energy exerted. Once spun up, the habitat can spin at a variable rate, and this mechanism can regulate the habitat's temperature. The rate of rotation can be increased if the temperature dips, providing the opportunity to spin at 2 rates for day and nighttime periods, reducing the problem of thermal shock. An air vortex will form at the center of the habitat, drawing water vapor from the water pocket above, leading to precipitation. This process is controlled using focused acoustic energy. Colonists of this world, with its quick days and low gravity, quickly realized that recreating the conditions of Earth on the asteroid belt would be a contrived way of accepting their new home. Instead, they sought to populate their vast underground cities with a diversity and density of life unseen on Earth. Palms, oversized vegetable vines, hibiscus, elephant ears, and saffron are all common sights in the habitat. Biodiversity and density are paramount here, since the available biomass is needed to sustain human needs. These colonies are self-sustaining and pruned to maintain and retain their efficiency. The short Cererian day has proven to be a boon to agricultural efforts. Many plant species present on the planet have been genetically modified to promote their auto-flowering characteristics. This reduces the reliance of flowering plants on their genetic photoperiod behaviors, allowing plants to photosynthesize and flower even with only periodic sunlight. While plant life represents the greatest biomass on Ceres, the world sustains freshwater and saltwater ecosystems and a diverse collection of organisms, including animals and insects. Biomass fostered by humans plays a crucial role in survival of the colony, in sustaining the habitat's atmosphere and providing food and material for industries. The cities on this world are invaluable scientific resources, providing direct observation of a multitude of organisms in various stages of acclimation to the low-gravity environment. Traits for giganticism in plants were found to pair well with the environment of Ceres, where highly organized vine-like plants, which often yielded legumes and melons, handled the intermittent sunlight well while also yielding large nutritive fruit. Plants with low levels of organization, such as wheat and potatoes, could only achieve practical yields if grown on fertilizers. Most of the farming techniques on Ceres rely on hydroponic or organic methods, so fertilizers are avoided outside of specific applications. Due to the design of Haworthia habitats, water, plant, and other aquatic animal cultivation is much easier. Most of the water inside these habitats is not under spin gravity, allowing the choice between organisms needing gravity and those that thrive without it in a shared environment. Underground caves and lava tubes on Ceres are different from their Terran counterparts. These were not formed from molten rock, but instead cryomagma. Cryomagma consists of volatiles warmed by the convection of ice under the planet's crust, and these may reach high pressures and temperatures. Cererian cryomagma flows consist of methane, water, ammonia, and carbon dioxide. Saying Ceres has lava tubes is more than a fair assumption. With the discovery of plume ejections from the dwarf planet's surface, all indicators for lava tube formation are evident. Even before we understood the composition of Ceres, we made assumptions about its geology based on its location and size. When the Dawn spacecraft made close observations of Ceres in 2015, it confirmed many of our assumptions about the planet's geology, although accuracy of specific models of the planet's interior have yet to be proven. We'll entertain in our thought experiment that these tubes are abundant and fairly stable. To know with certainty if these eventualities are possible, we'd need images of these formations breaching the planet's surface as we do in the case of Mars and the Moon. The Vandemia Planitia region is crosscut by a web of ancient lava tubes, many leading into briny underground springs. These locations are points of interest for industry, science, and exploration. Rare metals are abundant in the deep crust thanks to Ceres' partially fluid interior, which transports heavier elements to the planet's surface. The high cost of atmospheric gas means these tube networks are flooded with meltwater to accommodate exploration and contain volatile gases such as methane and helium. The habitats we've built on Ceres in our scenario are produced using primarily local material. Over 98% of the finished structure's mass originated from the body itself. What exactly is demanded to build Haworthia habitats, and what makes this design realistic and more viable than orbital alternatives? We're going to prove the viability of these large structures, as well as show how a diversity of local materials, as is seen on Ceres, greatly simplifies such grand projects. Megastructures, such as the O'Neill cylinder, must counter the various effects which arise from their operation. Structures which spin to provide gravity are not static and deal with precession, gyroscopic, and Coriolis effects. These factors mean that spinning habitats are dynamically unstable and must counter destabilizing forces to remain operational. O'Neill cylinders resolve this problem with counter-rotating sections to cancel out gyroscopic effects. Our Haworthia habitat uses a combination of buoyancy and precession motion to stabilize its rotation. The habitat is large enough to potentially experience a strong Coriolis effect, but this is negated by positioning of fluid storages in primarily microgravity regions of the habitat. The Ceres habitat will make use of high-strength, lightweight materials for its structure, including aerogel fabric, sintered aluminum foam, and polymerized regolith concrete. These methods will be proven on Luna, where similar materials are produced and used. Ground fill materials, such as soil and soil substrate, will be introduced once the habitat has been spun up to prevent mass from shifting from forces induced by the Coriolis effect. This allows the structure to be finished while under gravity, meaning mass distribution around the habitat will have less of a destabilizing effect. The construction materials needed must not only be transported and assembled, but most will be manufactured from raw local sources. Recall that regolith across the surface of Ceres varies substantially, with deposits of water, carbon, volatiles, and metals atop a foundation of water-interacted clays. Relying primarily on in-situ resource utilization for industry means that we should establish what methods are used to refine raw materials into industrial components. Quarried rock is a minimally processed product of mining, rock material with insufficient concentrations of useful chemicals. Extraction of water, metals, and amorphous carbon is accomplished by smelting. Alternatively, the regolith can be ground into powder and then baked in the thermal bath of solar energy, producing a powder which can be amended and filtered to produce various types of slurries for metallurgy and producing cement. Centrifuges offer another low-energy method to sort regolith powder by metal concentration for sintering. In this next section, material consumption needed for construction of the Haworthia will be broken down into the phases we previously outlined. Nuclear detonations produce a large amount of heat. The excavation site will hold on to this energy for a long time. With no atmosphere, waste heat has to radiate into space. The next operation continues while this excavation site is still quite hot. The radioactive regolith left on the walls of the pit will be treated with a carbon water wash which is applied at night. When daylight strikes the frozen wash, water boils off, scouring remaining radioactive dust and leaving a carbon residue. The carbon residue increases heat transfer rate of the hardened walls, and now the surface of the site is cool enough for the next phase. The gravel fill used in the bottom of the pit is quarried directly from debris produced by the blast. The excavation process creates a large field of debris around the site, which can be easily harvested when the radioactivity of the gravel is not an issue. The numbers we're dealing with here sound massive, and they are, but in the context of megastructures, these requirements are not daunting. 1.6 billion tons of iron, nickel, and ammonium slurry, plus nearly 1 billion tons of silicate rock, will be used to fabricate the habitat's single largest component. Humans are already familiar with projects requiring these amounts of materials. Australia alone produces some 900 million tons of iron ore per year for international markets. Assuming these materials are readily available, our timeline of completing this phase in under a decade is certainly possible. When dealing with future construction projects, we must adjust our expectations to allow for innovation, and realize many technologies still in their infancy today will be used to settle Ceres. The foundational disk will not be assembled from widely sourced material. Instead, it is created using nuclear smithing techniques which fuse the mass from normal regolith, which has been amended using iron and ammonia. This means production will be much faster than we expect, and the entire structure will be easier to move in Ceres low gravity, since we can build it immediately next to the excavation site. It is notable that Ceres is believed to have relatively little iron in its surface regolith compared to similar bodies, since heavier metals have tended to sink in the planet's muddy crust. The reality is that if conditions on Ceres are conducive, we can use novel techniques to produce the disk in a fraction of the time needed for incremental construction of such a massive object. If required material, like iron-rich regolith, is more sparse than we thought, we can simply build smaller habitats requiring less material. The disk has a volume of about 6 million cubic meters, with 85% of this volume occupied by lightweight concrete, and the remainder being a prefab steel beam and ferric slurry mixture. Iron-rich regolith is gathered from the surface of Ceres and just beneath its surface, where it is abundant after millions of years of bombardment by metal-rich meteors. The ratio of iron to ammonium salt will determine the amount of iron needed, and the required amount can be decreased if other useful elements are found. We've already mentioned using nickel as an alternative, but even aluminum will provide the heat conduction and hardness needed to fuse the disk. Prefabricated steel girders are brought in, either from space or from existing industry, and are assembled on site using plasma welding. Helium trapped in underground structures such as lava tubes and voids in the regolith are harvested and stored for current and future welding operations, but gas feedstocks such as helium are also available from operating nuclear power plants. We can be fairly certain of abundant useful gases in Ceres' underground caves due to her geological history. The fluid bearing's liquid is kept from freezing with heat and mineral salts. These minerals are a construction aid in case the project site does not have access to enough thermal energy to keep the fluid bearing from freezing during construction. This briny water can likely be found deep underground in many locations on Ceres, or can be produced from meltwater and local minerals. This salt will be mostly removed from the fluid bearing later, when the presence of an atmosphere makes heat management less of an issue. Vulcanized rubbers used to retain the fluid bearing are also employed throughout the structure to provide airtight seals. This material was chosen due to resistance to thermal shock and outgassing, but it requires replacement after heavy wear, making it a temporary measure to assist construction. Sintering operations will demand non-trivial amounts of nitrogen, oxygen, and carbon monoxide. While producing other finished materials on Ceres usually requires careful environmental control, sintering can be done in a simple furnace. As carbon in the sinter bed burns off, carbon monoxide will be produced and can be catalyzed with platinum into carbon dioxide. Metallic oxides from regolith sources provide the additional oxygen atoms needed for this reaction. Carbon dioxide is an important product to manufacture since it will represent a large portion of the habitat's atmosphere. The water plug occupies a volume of about 34 million cubic meters, but most of this volume is not water. Large transparent balloons of PFA plastics filled with inert gas function as a scaffolding for fluid, as well as reducing the amount of water needed. The formulation of these plastics allows them to resist degradation from thermal, UV, and chemical factors. 11 million cubic meters of liquid water are trapped in the water plug, with the gas balloons dominating space closer to the structural dome. These balloons weigh about 3 kilograms empty and inflate to a diameter of 25 meters. Each balloon contains about 820 cubic meters of gas at around 1.25 atmospheres. This means around 2,000 of these plastic orbs will be needed to complete the water plug. A lattice of protective window panes make up the structural dome, and consist of several layers of material. A layer of borosilicate glass is sandwiched between thermoformed polycarbonate sheets. A fine wire mesh is added between these layers to increase strength further. Industrial plastics are produced using a process of vacuum forming, followed by compaction, then sintering at over 700 degrees Celsius, then exposure to hardening solvents. These manufacturing techniques are ideal for the environment of Ceres, where most needed chemicals are available. Fluorine, carbon, and hydrogen are used to produce the PFA plastics. Oxygen, carbon, hydrogen, and chlorine are used to manufacture the polycarbonate plastic, which is finished using a locally manufactured phosgene gas derived from mined chlorine chondrite. The structural dome is flexible and can tolerate unplanned pressures using various mechanisms. Because of temperature control and gravity, large pressure is rarely exerted on the dome. Pressure is normally under 1 atmosphere, with slight variation across its surface. Of course, the dome must handle abnormal situations without compromising the habitat's atmosphere. Our design accomplishes this when most others might fail. The hexagonal window frames of the dome are engineered to withstand thermal shock with a layer of carbon painted on the exterior. The frames must also flex while maintaining overall water tightness. Excessive pressure on individual windows will cause them to first flex and then open up small vents which expose the water inside to the near vacuum of Ceres. This sudden drop in pressure provokes the exposed water to boil off, gassing into space. The rapidly expanding water vapor exerts an equalizing force which compensates for any excessive flow in the water column, while also preventing water from shooting off into space. The Haworthia habitat system is self-regulating and can vent relatively small amounts of water to equalize disturbances, as well as being able to react to habitat-threatening breaches. The plastic balloons have a self-repairing function as well as a structural role. If impacts damage an exterior window panel, these balloons will either block the damaged panel or will interrupt the flow of water, reducing the forces generated by an unexpectedly large breach in the dome. The colony's atmosphere is initially comprised of a mixture containing 5% oxygen, 5% nitrogen, 50% helium, 30% argon, and 10% carbon dioxide. In the end, the habitat holds a total pressurized volume of just under 154 million cubic meters, all gas generated by industrial activity or by tapping into underground reservoirs. The process of seeding conducted in Phase 5 will convert this environment into one with a similar amount of oxygen and metabolic gas as the atmosphere on Earth, but with most nitrogen replaced by helium and argon. The duration of the seeding phase depends on the growth rate of bacterial cultures and the maturation period of utilized plants. The intent in this phase is to allow the habitat's ecology to convert the atmospheric gases into a breathable medium while also producing soil for farming. Enzymes such as nitrogenase, lysate, and carboxylase, to name a few, are introduced and feed intracellular interactions with cyanobacteria cultures to fix atmospheric nitrogen and CO2. The feeding of cyanobacterial colonies with needed enzymes and gases generates a breathable atmosphere and other organic material. Once the atmosphere is mostly breathable, both microscopic and composting organisms, such as annelids, nematodes, and protozoa, are introduced to the habitat soil. The required amounts of these organisms will vary depending on how long they will be allowed to reproduce. A smaller amount of initial organisms will take longer to prepare the colony. Water cultures include krill, algae, and a large number of freshwater fish. Eventually, filter-feeding animals such as whales can be introduced to stabilize the aquatic ecosystem further. The propagation of artificial ecologies is an entire field of science by 2225, and the final phase of the construction of a Haworthia habitat is a proving ground for novel bioengineering technologies and techniques. Constructing Ceres habitats using the techniques we've discussed will have long-term effects on the dwarf planet's atmosphere. Dust will settle relatively quickly, but gases might take decades to completely dissipate. The passive heat stored in the planet's regolith also increases ambient temperature at the surface, in addition to heat produced by the colony. These factors have no real safety consequences outside of producing a little bit of dust. You've probably realized that, like O'Neill's cylinders, this design is widely scalable. While our scenario predicts a permanent home to hundreds of thousands of people, we could easily scale up this design to a massive million-person arcology, or down to a few specialized oases just a few hundred meters across. However, this concept has a minimum scale due to the limitations of the fluid bearing, and is most economically advantageous at large scales, as we've discussed here today. Go ahead and leave a comment if you have any questions or additions, and like and subscribe to help grow our audience. Thank you.